Time to move on to oxygen generators, concentrators, and spice cones. Now, oxygenation equipment is used in most high production recirculating aquaculture facilities because it offers you the ability to raise more animals in a smaller footprint. Okay? Plain and simple, anytime you're paying for a controlled environment space, you want the most production in the smallest area. That's math, that's business. Ambient air that we breathe every day is 20% of oxygen. It's about 79% nitrogen, another 1-2% in there, say 78-79% nitrogen, 1-2% of other chemicals. But 20, almost 79 of nitrogen. Those are the big numbers here. Oxygen generators constantly produce 92 to 96% oxygen. So you get a really high amount of oxygen compared to what we're going to get with an air compressor just using ambient air. When we're paying a premium price for a controlled environmental condition, it makes sense. So we can also use bottled or tanked liquid oxygen. We call it LOX, L-O-X. The viability of using this in your operation depends on several factors, including your distance from the oxygen manufacturing plant, the price that you're going to get it at, the scale of your operation, and your leasing terms and agreements with the oxygen company. So they're going to come similar to gas at a house or another location. They come and drop off a giant oxygen cylinder, and that is hard plumbed into your facility. You have a pressurized line, and you can feed oxygen out of that line. You calculate how much oxygen you're going to need on a monthly basis, and you have a contract, and you have a fill truck that comes out and they fill your tank up every so often on contract, so that they understand they're going to be liable if they don't meet a deadline and kill all your fish. It's really important to have things in writing when you get into volumes, and especially something like this. So the devices used to saturate the oxygen into the culture water will affect the efficiency and how much oxygen you're actually using per given volume of fish. So oxygen generators are typically sized based on the manufacturer's specification. This isn't something you're building. You're going to go buy it from somebody, and they've already done that research for you to make sure that it's going to perform the job that you need. So specifications will list the flow rate coming out of it and an oxygen concentration. So example, cubic feet per hour, CFH, at 92% oxygen. And that's how you will see these devices advertised. The specs will list pounds of oxygen per hour created, and the flow rate and the concentration. So we have these three factors, and that allows us to size this device for life support. Oxygen is injected through a venturi fitting under vacuum in most cases. So we'll talk about a venturi fitting here in a minute, but it's usually sucked from these devices into a pressurized saturation device. When you're talking about a large oxygen tank of bottled oxygen, liquid oxygen, of course that's under pressure, so that can be injected, doesn't need to be through a venturi fitting. It can be injected and metered in with a fine-tuned oxygen valve. So, for oxygen, we must calculate the total oxygen consumption for the fish, the biofilter, and the biological oxygen demand. So any other bacteria, any other demand that we have that's taking oxygen out of the water. We look at the efficiency of the device used that we're going to purchase to saturate this oxygen. Now, spice cones and oxygen concentrators are typically 94 to 100% efficient. Now, you may lose a little bit of that efficiency on the way back to the tank, depending on several factors or how that water is injected into the culture tank, but those are the hard numbers there. An LHO, which is a low head oxygenator, those contactors can be as low as 60% efficient, so they can be far less efficient, but they can also be up in the high 90s efficiency. A lot of this comes down to what the design is. For example, Freshwater Institute likes to use LHO contactors because of the way their design is. It works right in with their degassing column, and right after degassing, they can highly oxygenate, ozonate, and send back to the culture tank. For other people that don't have the head pressure that are going to drive this, or they have a specific oxygen loop, they can choose a species cone or a concentrator. Some of this is highly up to the designer, because again, we have many ways to get to the end product here. But size generator, then we size the cone, and then we size the water pump. Pretty easy, okay? The generator, we know X oxygen from our calculations from the fish. Then we size the generator off of that. Then we look at the generator produces so much. Well, the cone will tell us how much it will actually dissolve, so we can do that. And the cone will actually also tell us how much flow rate we need going through it. So it tells us the water pump size. So it's really easy. The hard part was calculating the oxygen in the beginning, and we did that, you know, two lessons ago. Not a problem. For quick reference, 1 pound of oxygen per hour will support 2,000 pounds of fish fed at 2% body weight daily at 78 degrees Fahrenheit. So if you're hearing all these numbers and you're trying to get wrap your head around, what is this actually going to do? What is this volume of oxygen going to do? Well, that's just a quick reference to put it all in perspective for you. Okay, so here is a species cone or an oxygen cone. You'll hear them called a lot of things. These are made commonly out of fiberglass. I've also seen them made out of steel, other materials. And what we have here is the inlet, okay? Here's a water pump. It pulls from our water source. It's going to go up. They've got a little flow meter here. This picture is from Aquatic Ecosystems website years ago. Water pumps up and it goes over, and then it's going into the top of this oxygen cone. Now right here at the top, you see there's a ball valve. The water would normally flow this way, but there's a T here that allows water to be side diverted through a venturi fitting and then back up and meet the main flow and go into this tank. Well, what that does is a venturi fitting works by increasing velocity enough that it creates suction. It creates vacuum pressure, and that will actually pull the oxygen from our oxygen generator into this device and into the water line to inject it into this tank. So just by the water flying past this fitting at a certain velocity, it will create suction. Now, if you don't have, all these venturi fittings have a required flow rate. If you don't meet the flow rate, it will actually shoot water out of the fitting instead of sucking water. So they're kind of temperamental. And that's why we have this water valve here. So we can open this valve all the way. It's normally going to bypass this. As we close it, it forces more and more water through here and will create more suction through that venturi fitting. So we can get it to fine-tune it right to where we need to by turning that valve and creating suction, and then we're pulling the right amount of oxygen into the device. Now typically right before here, we'll have a fine-tuned flow meter that gives us the CFH, or the flow rate of oxygen flowing in. And we can fine-tune that to the exact calculation that we've predetermined so that we're getting exactly what we want. So then we have our metered in oxygen. This is pulling it into the line, and it's injecting it into the top of this cone. Well, as the water comes into this cone, the velocity starts to slow down, okay? There's tiny bubbles in here. The bubbles are flying down in the water column, but as the velocity of the water slows, and as these bubbles hit each other, they're going to be pressurized into the water. The velocity slows, pressure increases, and these bubbles are forced into a compact area. They're going down and they're shearing back up as they form a bubble mass. So a bubble mass, wants to rise faster, comes up, and then it hits a faster force, shears apart, and comes back down. Well, this right here is where the action is happening. That's where all the bubble shearing is happening, and you're really getting the dissolving of that pure oxygen into the system water. By the time it gets down here, that velocity is really dampened. Look how wide this is compared to the top of this. So it's really slow coming out. Then it exits here, and we have super saturated water, or it may be saturated if you just have a low flow of oxygen. But this is where our product water comes back out and goes to your fish tank, directly to your fish tank as soon as possible. And you know, if you want, you could have 20 part per million coming out of there. When we know with an air blower, it's only going to be at maybe 8 part per million because we're using ambient air. So this is a great device. What you also have here on the end is a ball valve, and that ball valve has to do with the pressure meter here at the top. So we increase the pressure in this unit by closing this ball valve. So that makes the pressure in that vessel increase. And as we increase pressure, we get a higher dissolvability of oxygen. So that's another way that we fine-tune injection of oxygen here. We fine-tune the pressure to dissolve it at this point down here. So I hope that makes sense. Again, we bring it to a desired pressure here. If you ever think you're going to increase pressure and you're not safe, something like that, you don't want to hurt yourself by pressurizing this and blowing it up. We've seen people that just don't pay attention and they put too much pressure to these and they crack them. Well, put a pressure relief valve on there as well and set it to below your maximum PSI, and that way you'll never crack the vessel. At worst, you'll start bleeding water out of it. So we'll move on to the next slide, but hopefully that kind of explains the mechanics behind a species cone for you. Now, an oxygen saturator actually works on the same principles, same design specifics, pretty much, but it's a smaller footprint than the species cone because we're going to stage down, but we're not going to need that wide of a diameter base. These can be operated up to 40 psi when building out of PVC. If you buy them, they're usually out of a high density polyethylene, and you can get them up to 80 psi. If you buy them in a larger application, they could be out of steel. I've seen them up to 100 and 120 psi. Because again, the higher pressure, the more oxygen we can dissolve into that water. So normal operation though, between a lot of these devices, you can make them really strong. Normal operation is between 10 to 20 psi. Especially for most of the people learning this, most of your applications. Add an emergency, we just talked about this, pressure relief valve for increased safety, especially if you're making one yourself. Don't hurt yourself. Add one of these in, maybe another $20. You're saving a lot of money on the build anyways, building it yourself instead of buying it. So spend the money on safety. And never operate with ambient air, or you will cause nitrogen supersaturation. So we talked about 20% oxygen, 79% nitrogen. Well, if you suck in ambient air, you supersaturate nitrogen into the water, and it causes nitrogen gas bubble disease for the fish. Similar to a diver that dives down to 100 feet and then just comes up to the surface immediately and gets the bends. It's the same thing. They get nitrogen gas dissolved in their bloodstream and it can kill the fish. So you don't want to do that. Oxygen solubility is dependent on velocity, retention time, temperature, and pressure. Okay, so there's a lot of factors here. Flow in an oxygen saturator should reduce from your inlet velocity of roughly 5 feet per second to a second stage with a velocity between 1.25 and 1.75 feet per second. Then to a third stage with a velocity between 0.25 to 0.8 feet per second. So we drop from 5 feet per second to 0.25 to 0.8 feet per second. Pretty big reduction in velocity. And the reduction in velocity allows those air bubbles to hover, shear, and saturate into the water column. The bubble swarm happens at 1 to 1.2 feet per second. And if you actually spend the money, clear PVC is pretty expensive, but if you spend the money to build one out of clear PVC or make certain areas out of clear PVC, you can actually observe the bubble swarm happening, observe the insides of that oxygen saturator, and make sure it's doing what you want it to do. So, an oxygen saturator can dissolve roughly 1 pound of oxygen for every 62 gallons per minute of water flowing at the inlet. And this is using the rest of the design specifications, okay? Like we just said, the staged velocity reduction. But using that, again, roughly about 1 pound of oxygen per 62 gallons per minute of water flow at the inlet. We want to size the rest off of the velocities we just talked about. And some very common configurations are going to be as follows here. We've got a 1-inch pipe at the top, to 2-inch pipe, to 4-inch pipe at the bottom. And they're 2-foot long sections, okay? So 1-inch reduced to 2-inch to 4-inch. Then we have 2-inch to 4-inch to 6-inch, 2-inch to 4-inch to 6-inch to 8-inch, and then 4-inch, 6-inch, 8-inch to 10-inch. So those are some common configurations, especially this would be on an extremely large scale. 2-foot long sections of each stage there. And if you went in between on some of the flow rates, of course you could reduce the lower 10-inch stage to 1 foot or something like that. But all this has to do with what we talked about before, which is our reduction in velocity there and the flow of oxygen we're trying to pump into these. Of course, if you're going to build your own, it's going to take a little bit of dialing in, but if you understand how these work, then you can be confident that you'll be able to do that. So here's an example of some of the Pentair Aquatic Ecosystem part numbers. They sell oxygen saturators, and it gives you an idea of some of the flow rates that are capable going through these, okay? So they don't, 8 to 12 gallons per minute, 15 to 25 on the smaller, but they make some that go really big, 300 to 500 gallons per minute just for your oxygen loop. So that's a huge device, and definitely if you're going to that scale, you're not building stuff yourself. You're probably going to buy this. So, check out the specifications. If nothing else, you can look at them to give you an idea of what their flow rates are and what their saturation points are at different pressures, and compare that to what you're building. So it gives you a little bit more in-depth information, just like the WMT gives us a little bit more information about the radial flow settler design. And there's a picture of some of their saturators that are made out of high-density polyethylene. Now, there's also, I was introduced to an in-tank low-head oxygen saturator from Richard Baptiste over at Harbor Branch University. Richard's an awesome guy, works doing really good research in multi-trophic aquaculture right now down at Harbor Branch University. And he came to one of my courses years and years ago when I still worked for Aquatic, and we've stayed in touch ever since. But he introduced me to this. Again, hadn't heard of it before I was talking to him, and he was nice enough to allow me to present it to you guys just to open your mind a little bit and show you what else is possible. So these are not as efficient as a pressurized vessel with a valve on the bottom, because we know increased pressure means increased oxygen saturation or dissolvability. But they are a great option for low-head systems. They utilize velocity reduction and water pressure from the depth of the water that you're placing this into to actually dissolve the oxygen. And here's a picture of one. It's on its side, and you can see here's a 2-inch, goes up to 4-inch here, where your bubble swarm is going to be, and you can see the clear pipe so they can observe. And then it goes up to 6-inch here, okay? And out the bottom right there, they've got a 45-degree angle, and that's actually going down, so the water has a downward force into the tank, and you keep the high oxygen water in that tank as low as possible for as long as possible. So it's going to mix, but you don't want to inject your high oxygen water right at the surface of your culture tank, because if you've got 20 parts per million oxygen, and it's coming right at the top of your culture tank injected in, and it's only 8 parts per million outside, well, it's going to diffuse out rather quickly. So to keep it in the tank as long as possible for the fish, we want to bring it into the bottom. But you can see above this is actually a union. Above this is the injection point for the oxygen. They just have unions in there so they can take it apart for cleaning. But what a wonderful design. They have 3 of these in some large tanks that run Red Drum and Pompano in the past, and they work great. He wouldn't be using these in large-scale research designs if they didn't work. I love the design. Okay, aeration and oxygenation continued. Now, there are other factors to consider when sizing aeration or oxygenation systems. Oxygen saturation is dependent on temperature, pressure, and salinity. Usually calculations assume standard conditions. They assume one condition so that we can standardize that and come up with, you know, a table of values. But if you are not within the standard conditions, you need to adjust for that. So usually calculations assume that aeration and oxygenation will be done at sea level, which is 1 atmospheric pressure, at 72 degrees Fahrenheit, and at 0 salinity. But again, that's not always the case. We could be at 5,000 feet elevation, all of a sudden we're at 5 atmospheric pressure. If we're raising tilapia at 86 degrees Fahrenheit, well, that's going to be pretty far off from our 72 degrees Fahrenheit. So things can change. We're not talking a lot about saltwater RAS or saltwater aquaponics in this, but again, if you're doing saline water, you could also have a difference in oxygen diffusion there, or saturation. So if your operation is going to be in a location where it's affected by high altitude, so high altitude lowers the dissolvability, or by high temperatures, or by saline water, you need to plan accordingly. So we'll move on to the next slide here. And just throw this out here, when sizing blowers for aeration purposes, you want to go ahead and deduct 4% of the volume and pressure from the rated performance for every 1,000 feet above sea level. So that is a real easy calculation just to give you a visual, realistic idea of how much performance you're losing. You know, if we go up 2,000 feet above sea level, well, we're at 8% volume and performance dropping. That's not huge, but it is significant. And if we were to go again to 5,000 feet, well, then you're at, you know, what, 20% volume and pressure going down. You might have to size up an entire unit size just to overcome for that and to compensate. So very important to remember. Oxygen solubility versus pressure in fresh and salt water, okay? That's this table right here on Engineering Toolbox. So click this link and you'll see tables that show you what's the solubility versus pressure and versus salt water and fresh water. So there's not the in-betweens, but it shows you in fresh, and then it's either, I think it's 32 parts per thousand or 35 part per thousand salinity, but it's labeled on the chart. Okay, and this next chart shows you oxygen solubility versus elevation. So it's laid out a little bit different. There's a lot of charts on here, but if you click on this link, you will see different elevations and what the oxygen solubility is to be expected at that elevation. And then on this chart here, I went ahead and laid out, you've got your temperature here, okay, in Celsius. You've got 0 to 17 and then 18 up to 35. Cut the bottom row off on the screen here, but you've got it on the presentation in front of you. But this is basically the temperature versus the oxygen saturation point, okay? So your highest oxygen saturation point using ambient air. If we're just using, say, a blower or an air compressor, something like that. And just to show you the trend, you can see at lower water temperatures, so 0, 1, 2, 3, lower water temperatures, you can dissolve more oxygen into the water. And as the temperature rises, you go 14, 13, 12, 11, 10, 9, you get all the way up to, say, 28 degrees Celsius, you're at 7.75 as your maximum milligrams per liter, maximum oxygen parts per million that you can reach using ambient air. That's all you can get in the water before the air you're putting in diffuses back out with the environment. That's it. Now, with pure oxygen, of course, we can go, or an oxygen generator, we can go far above that. But this is what you can do just off the temperature. Gives you a good idea. Sometimes in pond aquaculture, fish will be fine for a good amount of the year, and then in some of the hottest days of the summer, they'll have a lot of fish gasping for air at the top of the water, or they'll have fish kills, and in people that aren't, don't have ponds aerated properly. And that's exactly why, is because when that temperature drops, it can hold less oxygen. Well, the fish aren't going to drop weight just because the temperature drops. They're still going to consume the same amount of oxygen, and actually more at a higher temperature. So you know, that just gives you an idea of what could happen in certain situations just due to a temperature fluctuation. Here is it laid out the on a different scale here. We've got oxygen concentration over here on the left, and then we've got the temperature on the right. So again, same thing, temperature versus DO, but this blue line is freshwater and the green line is saltwater. And I really just wanted to lay this up here really quickly to show you. We're not looking at night and day, so this isn't a humongous amount of difference. Let's say, again, well, let's go up to something realistic. 20 degrees Celsius here. We've got about, what's that, 9 is going to be our dissolvability in freshwater, and we've got about a little over 7 in saltwater. So it definitely affects it, but you can see here, as we get warmer, it affects it a little bit less. These lines come together, and it's not that hard to account for the difference if you were ever to do anything in saltwater, as long as we plan for it before we install the equipment. So we'll move on now to degassing carbon dioxide. Carbon dioxide is introduced to the water column from fish and bacteria respiration. So they're taking in oxygen, respiring CO2. In systems utilizing aeration, so a blower, any ambient air, and if we're stocking in the 1/4 pound to 1/2 pound per gallon range, which is 30 to 60 kilograms per cubic meter, degassing filters are generally not necessary. We've got enough aeration happening by cascading waterfall flows, you know, through the system, through the filters, by aeration in the biofilter, etc., that we off-gas naturally the CO2 that's produced from feeding the fish. When densities are pushed past these, so really when you get into pure oxygen design or oxygen generators, CO2 will build up faster than we off-gas it naturally, or than it off-gases through general means. And when you use oxygen, there's a lot less breaking of the surface tension of the water. Aeration bubbles are constantly breaking the surface tension and off-gassing. You don't really get that in oxygen. You only get it from the water flows and water moving, not so much updrafts of bubbles. So, for every 1 gram of oxygen consumed by the fish, 1.38 grams of carbon dioxide is produced. I guess we could say by the fish or bacteria here. Fish tolerance depends highly on species, so we need to look up what we're growing, tilapia, trout, salmon. Look that species up and look at its tolerance. It's very easy to do, and if you're investing all the time into this, you know, a couple clicks isn't too much more to ask. So you want to do a lot of research on the specific species, because we're trying to lay out guidelines here, you know, for designing and engineering of the production systems. But if you want to do it even better, you get the species specifications, and we really detail it to what that species needs. So back to this, tilapia and striped bass have been shown to tolerate upwards of 60 milligrams per liter carbon dioxide. So they're not as susceptible to it. They still put on good growth, they still have good feed conversion ratios, and it hasn't shown to affect production in a negative way where they need to degas below these levels. While trout, we move over to here, a little more sensitive fish. Think about where it lives. Streams, rivers, a lot of cascading water, a lot of clean water. So they actually run values in the 9 to 30 milligram per liter range. They're not a dirty water fish. Trout like cleaner conditions. So because of that, we would account for that. Research the specific species and identify acceptable levels. So as far as designing degassing columns for degassing carbon dioxide, it's not very easy to predict the removal rate because there's a lot of factors at play here. A packed column is widely used. Again, we could have an aerated square tank and that would be considered degassing. But a more efficient way is a packed column degassing unit. Manufacturers, when you're purchasing these, they'll actually give you the estimated removal rates per surface area of media. So we use their numbers to size. They're selling you the equipment, they've already done tests on it to see what the actual removal rates are, and we can be confident, as long as you're buying from somebody reputable, that those numbers are going to work in your system. So we size based off of their given numbers. Countercurrent degassing columns are more efficient by blowing air upwards against the falling water to help strip the water of CO2 and the column of CO2, which is then sent out of the facility. So you've got to think about a packed column. What this really is, without seeing a picture right in front of you, is we pump the water up to a top source, and we have a packed column of plastic with little holes, and the water is dispersed and has to flow downwards through one or several levels of these large areas of plastic media with holes through it. This breaks the water up, allowing more surface area of water to air ratio, and the higher the ratio, the more the CO2 is going to want to come to equilibrium and come out of the water column and go into the atmosphere. So that's really what these are doing. We bring water up in one massive amount into an area, we spread it out, let it trickle down and have more surface area and interaction, and that does our stripping for us. So a countercurrent degassing column works the same way, but we actually pump air upwards. So while all this water is cascading, think raining down, we've got air flying upwards against it, and that actually gives it more surface contact to air. So it's the same surface area, but what you get is you get a lower concentration of CO2 in that column. So as the water falls, CO2 comes out, it's still in that general vicinity. By hooking up an air source going in the reverse direction, it strips that CO2 out of the air so that it's not redissolved into the water, say at the bottom of that column, or where you have contact with water again. So it really improves efficiency just by moving that out. And also, in any of these situations, you're dealing with such high density of CO2, we have to remove it from the water. Well, we also need to remove it from our facility. That can become dangerous to workers. So at the top of these stripping columns, we will actually pipe that right out of the building so that you don't have a buildup of CO2 to dangerous levels inside your facility. Okay, so the best place for a degassing column is directly after the biofilter. So we've already got production after the fish culture tanks, then it goes through the biofilter, you get production from the, the bacteria doing the ammonia conversion. So you get the highest levels of CO2 right there. After the biofilter, that's when we want to actually degas that water, and that's where we place the degassing column. So in general, a CO2 degasser is designed with the following parameters. Again, this will change depending on your type of packing media, depending on maybe your fish species, depending on the flow rates and how much we need to degas. So there's other things that come in here, but this is the general specifics on how we size it. And we have a hydraulic fall of between 3 to 5 feet, or 1 to 1.7 meters. So the fall needs to be that long, okay? The hydraulic loading rate, how much water we flow through that, is going to be 25 to 35 gallons per minute. And that's per square foot, okay, of media. So that gives us a loading rate. This tells us how much the fall needs to be. This tells us how much media we need per volume of water. So that's kind of our key components there. And then we have an air to water ratio of 5 to 1 to 10 to 1. Meaning if we're at least in the 5 to 1 to 10 to 1 ratio of air to water, we will get CO2 leaving solution and going into a gaseous form and leaving the water column, which is exactly what we're intending to do. High porosity packing material in the column is what's preferred. We really want to break up the water to get as much of it exposed to atmospheric air as possible. Very similar to a biofilter where we want as much surface area for the bacteria to fix to attach to and process our ammonia. Well, in this case, we want as much surface area so that we get the diffusion of CO2 out of the liquid. If designing large facilities, I would really invest in the aquaculture engineering book. They have design software in the book that is very simple to design for larger facilities. So again, if we're talking $500,000, $1 million, spend a couple $100s on this book. They have software that will be useful to you. It comes with, interactive software. It's worth the money. I'll put my name out there exactly. A lot, as we've mentioned, of the aquaculture engineering is coming directly from this book because that's kind of what we all look to as the industry standard. This is the knowledge that we know works and that has been proven successful, and that isn't people guessing still and trying to figure out how the processes work. These we know work, and that's where we want to start. And that's it for this session. Again, if you have any questions at all, please email me, ryan@collegeofaquaponics.com, and I will be sure to cover those questions in our weekly question and answer session and make sure you get all the information that you need. Thank you very much.